Okay. Okay, hello everybody. Welcome to my talk. I'll be talking about Spark and Spark streaming in particular. I'm coming from SV Group, one of the sponsors of the conference. My name is Petar Zečević, and I'm organizing monthly Apache Spark meetups in Zagreb. The next meetup is on March the 1st. The guest will be the lead architect from Farmeron, which is an interesting company, so come around if you're interested. You can find us at the link, this link. I also wrote the Spark in Action book. Some of you have applied for the lottery. We will give away 2 books, so I think right here after the talk. So good luck. The agenda for today is I'll be talking a bit about Spark in general, what it can do for you, how it works, and then about Spark streaming, obviously. And I'll show some examples of code, and I'll show a demo how you can build a simple application, Spark streaming application. So first of all, indulge me. I was here a year ago, and not many people were familiar with Spark, so I'd like to know where you stand today. So first of all, can you raise your hand if you're planning to or are using Spark in production maybe? Okay, one, yeah, okay. Thank you. I've played around with it at least on my laptop. Couple of guys, okay. And I've never used, I guess that's the rest of you. Okay. So I'll try to explain more generally about Spark. It's a distributed, general-purpose, large-scale data processing engine. So if we unpack this definition a bit, distributed obviously means, I guess you know, that it runs on many machines. It runs on some kind of a cluster. And the computations are parallelized. The programs that are running on Spark are running actually on the cluster as a distributed computation. And the program is serialized and sent to where the data resides, unlike the traditional programming where you read some data from a database, process it, and send it back to a database somewhere else. Here you would send a program to the data, which is much more efficient, and if you have large amounts of data, it really cannot be done. It's general purpose, which means that it's used across industries. It can be used in many different settings and environments. It reads any kinds of data and writes any kind of data. Generally, whatever Java, Scala, Python, or R can do, which are the versions of the API. Spark APIs is available in all these languages. It's large scale, so when we say big data, everybody thinks of these guys, but it's not just social networks, it's also banks, healthcare, biology, telecommunications, weather, astrophysics, and so on. But you should have, if your data fits inside a relational database or inside one machine, you probably don't need the Spark or distributed computing engine because there's always some overhead with organizing work across the cluster, serializing tasks and data and so on. So if it fits on one machine, you can build a clever Linux script or something, databases which have indexes, they're optimized for joins and so on. So much more performant to do it on one machine. But if you think that in the future you might start getting more data, it might make sense to start investing in implementing Spark or similar framework right away. And it's a data processing engine, so obviously it's about processing data. It's not your ERP system, it's not for storage. It stores data in memory temporarily, but it's not for storing data. Spark doesn't store itself, the data. It can store it in the relational databases, in file systems and so on, but not Spark itself. It's not your OLTP system. For example, you don't use it to update little bits and pieces of data similarly to I don't know, a banking application or some online store. You wouldn't do that with Spark. It's more meant to as OLAP processing engine analytic, where you take larger bunches of data and process them together. And it's not for reporting or visualizations. It's used for preparing data for reports and visualizations, but not doing them on its own. So why would you use Spark? It's fast. It can be 100 times faster than MapReduce. Its previous successor, which is still in use today, but Spark keeps. It's kind of obsolete today. Spark has gone superseded MapReduce. It's got simple and concise API. So if you've been to Alex's talk today about Java streams and lambdas and so on, it's similar to that. Scala can be, you can write a one-liner, as he said, which is really effective, and also in Python and so on. And it's a unifying platform. What that means is that it's got really feature-rich API. So I'll show you in a bit. And it has gone mainstream because today all the major Hadoop distributions include Spark. There's a bunch of projects and products built with Spark. The community is huge, and it's really developing very fast. And for example, IBM opened up a Spark Technology Center in San Francisco a year or two ago, and they have 600 people working only on Spark. So the basic architecture would be you have some kind of client JVM. You start your program, and it constructs a driver. Driver is the main class that you use for communicating with the cluster and executors. And the cluster can be Spark standalone cluster, Mesos cluster, or Hadoop Yarn, which is used only for bringing up allocating resources for executor JVMs. So that's a number of threads that they can use, amount of memory, number of executors, and so on. And there's each executor has several task slots available for executing tasks, which are just Java threads. Those blue ones are tasks already executing. White ones are vacant task slots. And this doesn't say anything about the number of physical machines it's running on. This is a logical picture, so it can be on a single machine on your laptop, which I'm going to show you later, or five physical machines. So the functional components of Spark API, the main components are these. There's a Spark core, which handles unstructured data and works with RDDs. This is the main abstraction in Spark, resilient distributed data set. It's basically a distributed collection of data. So you work as similarly to Scala or Java collections, but the data is distributed across all those executors. Each of them has a partition of that data. And there's Spark SQL, which works with data frames. Data frames have, similar to database tables, they have columns and rows, and it's structured data which you can manipulate and query with ANSI standard SQL. Then there's Spark Graphics, which enables you to organize data in graphs and run graph algorithms on them, such as PageRank. Then there's machine learning libraries, ML and MLlib. All of the most often used machine learning algorithms are there. And there's also Spark Streaming, which works with these streams. So about Spark Streaming, the basic idea is that you have some sort of data input, be it Kafka, Flume, Kinesis, S3, simple files, or TCP/IP sockets. Then it keeps coming in continually, and you would Spark actually splits the data in time periods, which creates mini batches. So you have a time period, which is mini batch interval. And in each mini batch, you get one RDD, distributed collection, which has all the data that arrived during that time slot. And then from that point on, you work as though the data came from a single place. It's not as though it's not Spark streaming. It's not real time. You work with it as though it's a batch operation. So you can use all other functional components from Spark, machine learning graphics, SQL, and so on, even non-Spark functionalities. And then you would probably save the results somewhere to an HDFS, a relational database, back to Kafka, or some other place. So the features in a nutshell would be, it works with discretized streams, these streams, and they represent a string of RDDs. So you write a program on a discretized stream, and it gets executed for each RDD in each mini-batch interval. There are receivers for various sources, of course, and there's a special Kafka direct connector, which works so that it opens up one connection to Kafka topic for each partition of the Kafka topic. So it can read data more efficiently, and it enables you to create that you write programs that process data exactly once, so that you don't lose messages and that they are not processed several times. It also enables you to save computation state over time. You can preserve some global state in the memory during the execution of the program. You have window streams. I'm going to show you examples later. And you can join streaming data with static data from wherever they might come from. There's also back pressure. That means that when Spark detects that your program is not able to cope with the data that's coming in, so your processing time is longer than the mini-batch interval. That means that by each mini-batch interval, you keep lagging behind the data that's coming in. Then Spark, if this feature is turned on, then Spark stops reading the data from the input and allows your program to recuperate, to start working again normally. And in general, Spark streaming is for latencies of half a second and upwards, because you can specify a lower batch iterations times, but most often Spark needs to organize work around the cluster, and mostly under half a second it doesn't work. You cannot get really good performance, but for 99% of cases, I think you don't need latencies below half a second. You can really, I think, if you think you have such a use case, you might think again and realize that it's really maybe not necessary. And structured streaming, that's new in Spark 2.0, which enables you to view the streaming data as though it's coming into a database. It keeps getting inserted in the same database table, and you work with SQL, NCSQL. You work with those data as it's in a database. It's still in early stages. I think Databricks, they say they have it in production, but I'm not sure. So I'm going to show you an example of word count. There's always a word count in each Spark presentation, because it's so actually not a trivial thing to do. And it's simple enough so that you can see the main point. So the Jupyter notebooks, I think, is anybody familiar with Jupyter? Yeah, okay, some of you. So it's it was used mainly first meant for running Python programs. You can write your program in these cells, execute them in the kernel, which is running in the background. I have Apache Tori here running for writing Scala, and that's actually Apache Spark cluster in the background on my virtual machine on my laptop. So when I execute these cells here, I'm executing them in a Spark shell on a Spark cluster. So for example, here we can get the Spark connection. SC variable is the Spark context. You have that pre-configured in each Spark shell. So you get config, get all for each print line, so we can see what configuration is current for our Spark application, for example. Then normally in your normal program you would construct the Spark configuration and Spark context yourself like this, but in the Spark shell which we are running here, it's all pre-configured for you. So the next step would be to construct a streaming context which takes the Spark context and the duration of the batch interval. In this case it's 1 second. So it's okay, we done that, and we are going to read data files from a folder, home Spark TMP, and Spark works as it looks at a folder and it monitors a folder. When new file comes in, it reads that file and distributes the data from that file along the cluster. So it doesn't take into consideration the files that are already in the folder. It only processes those files that are created afterwards. So this file stream object here is a discretized stream, and its RDDs, or the collections that you get in each mini batch, have as elements lines from the files from this folder. And you can now call flat map, which you should be familiar to those working with Java streams or Scala. It transforms each element into 0 or more elements. So in this case, each line is split by white space, and we get several more elements. So actually we get words from each file. Then we filter out those that are empty. If they equal, if they're empty, they're not. We filter them out, and then we map each of those words into tuples of key and value. Key is the word itself, and the value is just 1, and that means that we attach a number 1 to each word in the file, and then we reduce by key, and that means that we group by key first, and then execute this function on each of the values of the grouped keys. And the result is just 1 value for each distinct word. In this case, we just sum up all the ones. And the result is that we get, for each word, we get the number of times it occurred in the file. Or files, if several files came during the mini batch. And finally, for word counts, the resulting D stream, we say that we want to print line the top 5 words by a number of occurrences. So I will execute this. Nothing happens still when I execute this, because Spark just remembers the program. This stream is just an RDDs, and these streams are just programs. And not until I say SSC start that the program will get serialized, sent to the executors, and then the computation will start. Okay, now it's started in the background, and I can go to a Linux shell. Let me remove this. I don't know if you see this. I hope you see it, but it's not that important. I'm just copying some, for example, Spark license file to this temporary folder that Spark is monitoring. So when I copy this file, it immediately picks it up and counts appears 102 times, of 65 times, and so on. If I so that's a one-time thing. For that mini batch, it calculated those numbers, and that's it. If I copy a second file, for example, notice, it will read those words, count them, and so on. and that's it. The computation is running in the background, but those files are processed. So I can now stop this Spark context, streaming context. If I say false, that means I don't want you to stop also the Spark context. I want you to keep running in the background, but just stop the Spark streaming. And yeah, okay. Let me remove these files. I'm going to show you now the idea behind Spark streaming saving state. So you have time going from top to bottom, and you have each mini batch new set of data coming in. And in each D stream, you have a new RDD, and you have an option to update a global state during all of this time. So the color nuance of this state is changing, so it's updated. And in each mini batch, you can output some different results. So this is how it's done in the code. We can, first of all, it's important to set the checkpoint directory, because when you update the shared state, in that case, Spark needs to rerun the same code all over all the time, and the stack trace of that process keeps growing. So if you run it long enough, it will report a Stack Overflow error. So by this mechanism, Spark can save the state of the RDD or D stream, and save the data it calculated so far, and the whole stack trace and all the steps that it took to get the data. It will save it in memory. If some executor fails, it can rebuild that RDD along with its data. So it actually breaks the stack trace at that point and replaces it with read the stack trace data from a file. So that's the first thing here. And the second thing I want to say here is that we can override, since we're running this in a Spark shell, we can overwrite the previous SSE variable here. I don't know if you noticed, but never mind. So we're creating a new Spark streaming context, and this time with 5 seconds of batch interval. And this time we're going to count the number of words, each number of times each word appeared in all the files since the beginning of the computation. So the first line is the same. We're reading monitoring the folder. We're calculating, this is the same, word counts and all the rest. What's different is that now we can call the map with state function here and provide it with a function update count state. And it actually tells Spark how to join data that came from during this mini batch with the data in the global state. And the global state contains, you can see it here, it contains a long. So it's a count of all the count, and the word itself is a string. So for each word that came in during this mini batch, and for each count, for each word that has a count in the state, it will call this method. And if the state exists, we will take the current state from the current count from the state and update it, add the new count and update the state. If it didn't exist, the update will create the new state for that word. And when we do that and call state snapshots, the resulting D stream will contain all the words and their counts from the global state. And now, if we print out the top 5 words, we'll get the words from the whole streaming computation. So let me execute this. It will also start the streaming computation. And now, if I copy license file, You will see it appear here. It takes a bit longer because it's 5 seconds now. So it's the same as before, but the difference is that it keeps repeating itself because it's reading it from the global state. And if I copy the new file, notice it will change. So and that's what you would expect from, I hope, from my previous description. So we'll do it, stop the streaming computation again. And the last example has to do with windowing. So the window is several mini batches long, and at each it moves by slide duration. In this case, its slide duration is 2 mini batches long, and at the end of each slide, the D stream is computed, and you get some results. And it computes the data from the whole window. So you can say that a normal D stream is just a special case of windowed D stream because it's a window stream of window duration of 1 and slide duration of 1 mini batch, right? So if we would do that with code, we would need a new streaming context again with 5 seconds, and again the reading, monitoring the folder code is the same, and filter and all the rest, except for this function, calling of this function. We say that we want windows of 20 seconds, which must be a multiple of the batch duration of 5 seconds. So then we map all those words and do all the rest, it will take into account the data that came from the last 4 mini batches. Every time that we recompute this stream, it will take 4 mini batches worth of data. So it's just one line makes the difference here. Now when I start this computation and clear the folder and copy the license file, we need to wait for maximum 5 seconds for a result. Or what's wrong? Let me try one more time. Okay. License. Okay, there you go. The license file is here, and it keeps remembering this file and these results for 20 seconds. If I add a second file, where is it? Notice. It will change as before, but after 20 seconds, it will change again because it will quit remembering the last file. Right, so that's it in a nutshell, what I wanted to show. I have only half an hour, but in the book I have a more complete example which shows a moving graph with results from analyzing clickstream data. You can check it out in, I think, chapters 6 and 13, and there's GitHub code, link to GitHub up there. All the code is online. And there's also a virtual machine on the book website at Manning. I just wanted to say for a Kafka producer, you cannot if you're writing your data back to Kafka, you cannot just open a connection from one place and then ship it off to executors, because the connection is not serializable. So you would need to open connection from executors themselves. And this code here can help you to start just one producer per JVM. So no matter how many tasks and jobs each executor, Spark executor executes, processes, it would use just one Kafka connection for sending data. It doesn't have to open up a new connection every time. So you have that also online. And that's it. We're hiring. If you'd like to work with Spark, maybe, you can contact us. And yeah, I don't think... do I have time for questions? No. So we're gonna just... we have a lottery for 2 books, so we can do that now. Okay, Sanya will do it. Huh? You're gonna draw, or
You're gonna draw.
I'm gonna draw?
You're a lucky hand.
Okay.
Just
Okay. Okay, there's one. We'll have to hurry, I think. Dražen Jurkin. Ja. Može. Čestitamo. Evo, ako hoćete, potpišem poslije, pa... Ok. Ha?
zvijezda.
Pa to se tak radi, valjda, ne? Ok, the second one. Jednu damu. A sumnjam da ima dama zainteresiranih za Spark, ali nikad se ne zna. Nemanja Marjanović. Ok. Evo. Čestitam. Ajde. Ok, hvala svima. Thank you very much.